Hi everyone, this is Professor M. Science, and today we will discuss the ground state of the hydrogen atom in another one of our videos on rigorous quantum mechanics. The hydrogen atom is an iconic system in physics. For example, it is the simplest of all elements and also the most abundant element in the universe. The hydrogen atom is also one of the very few systems for which we can actually solve analytically the associated quantum mechanical equations. The details of the mathematical derivation of the hydrogen atom energy eigenvalues and eigenvectors in one of our videos that is linked in the description. What we will do today is to explore some of the key properties of the ground state of the hydrogen atom, which are used as a benchmark for all other systems. Specifically, we will discuss the ionization energy, which is the energy required to dissociate the proton and the electron when the hydrogen atom is in the ground state. And we will also discuss the typical size of the hydrogen atom, which is given by the so-called Bohr radius. So let's go! The hydrogen atom is made of two particles, a proton and an electron. We can draw this by considering a coordinate system and describing the proton with the corresponding position operator like this, and the electron with the corresponding position operator like this. Now, of course, the proton and electron live in a 3D space, but for simplicity, I'm just including 2 dimensions in this schematic. We know from the introductory video on hydrogen that the relevant physics of the system is encoded by the relative motion of the proton and the electron, which is captured by this relative position vector. Based on this, we describe the hydrogen atom with a one-particle relative Hamiltonian H. The Hamiltonian has a kinetic energy term and a potential energy term. In the position representation, we can rewrite it with the usual kinetic energy term and the potential energy term, which has the form of a central potential. For a full derivation of this relative Hamiltonian, I refer you to the introductory video on the hydrogen atom. But just as a quick reminder, mu here is the reduced mass of the system and is related to the masses of the proton and electron by this equation. P here is the relative momentum given by this expression in terms of the individual momenta of the proton and electron, and R here is the relative position, which, as we show in the diagram, is given by the distance between the proton and the electron. Now, this relative Hamiltonian is the key to understanding the hydrogen atom using quantum mechanics. Specifically, we can write the eigenvalue equation of the Hamiltonian like this, where, as usual, these are the eigenvalues and these are the eigenfunctions. The eigenvalues are labelled by a quantum number n here, which can only take positive integer values. The eigenfunctions are also labelled by n and 2 additional quantum numbers, L here and ml here, which are associated with orbital angular momentum. We have solved this eigenvalue equation to determine all bound states of the hydrogen atom in a series of more mathematical videos that are linked in the description. And what we want to do today is to focus on the ground state energy and wave function, which will allow us to expand our conceptual understanding of the hydrogen atom. So let's go straight to the ground state energy. Remember that we can write the energy eigenvalues of the hydrogen atom as equal to minus the ionization energy over n squared. And remember that the ionization energy is given by this expression in terms of the reduced mass and of fundamental physical constants. From this general expression, we can write the ground state energy E1 as equal to the negative of the ionization energy, and explicitly we get this. Let's put some numbers into this expression, and let's start with the reduced mass mu, which we can write using this expression in terms of the electron and proton masses. In SI units, the proton mass is equal to 1.673 times 10 to the minus 27 kilograms, and the electron mass is equal to 9.109 times 10 to the minus 31 kilograms. If we plug these numbers into the expression for the reduced mass, we find a value of 9.104 times 10 to the minus 31 kilograms. Now, if we compare the reduced mass here with the electron mass here, we see that they are very close to each other. And that is because the proton mass is several orders of magnitude larger than the electron mass, and as we discussed in the introductory video on the hydrogen atom, the relative motion of the proton and electron in hydrogen is, to a very good approximation, describing the motion of an electron around a stationary proton. To evaluate the ground state energy, we also need the numerical values of the three fundamental physical constants. The fundamental charge E is equal to 1.602 times 10 to the minus 19 coulomb. The permittivity of free space is equal to 8.854 times 10 to the minus 12 meters to the power of minus 3, kilogram to the power of minus 1, second to the power of 4, and ampere squared. And the reduced Planck constant is equal to 1.055 times 10 to the minus 34 joules second. Plugging these numerical values into the expression for the ground state energy of hydrogen, which is equal to minus the ionization energy, we get minus 2.176 times 10 to the minus 18 joules. When we work with atomic systems, the SI unit of energy, the joule, is actually not a very useful unit because we end up with very small values like the one that we just got. Instead, we typically use the electron volt as the unit of energy, which is abbreviated as EV. 1 electron volt is defined as the kinetic energy gained by an electron in vacuum, starting from rest and accelerating through a potential difference of 1 volt. With this definition, 1 electron volt is equal to 1.602 times 10 to the minus 19 joules. And using this relation, we can convert the ground state energy of hydrogen to electron volts, obtaining a value of minus 13.6 electron volts. Right, so what does that number tell us? Remember from the earlier videos on hydrogen that the zero energy corresponds to a proton and electron that are infinitely apart. In this context, negative energies correspond to bound states, and the ground state energy being negative means that the ground state of the electron-proton system is that of a bound hydrogen atom. The precise numerical value is telling us that if we have a hydrogen atom in its ground state, then we need to provide an energy of 13.6 electron volts to unbind the electron from the proton. The minimum energy required to remove an electron from a neutral atom in its ground state is generally called the ionization energy, and this explains the name that we have given to EI, which we initially introduced as a mathematical shorthand. Let's now move to the ground state wave function. Remember that we can write a general eigenfunction of the hydrogen atom as equal to a radial part multiplying an angular part. The eigenfunctions are labelled by 3 quantum numbers. N here, which we've seen is associated with the different energy eigenvalues. L, which is the quantum number associated with the total angular momentum of the system. And ml here, which is the quantum number associated with the z component of angular momentum. The angular part of the eigenfunctions is given by the spherical harmonics, while the radial part takes a rather complex mathematical form that we explore in some of the other videos on hydrogen. So, the ground state corresponds to n equals 1, L equals 0, and ml equals 0. With these quantum numbers, the radial part of the eigenfunction, which is R10, is given by this prefactor times an exponential. the angular part, y00, is given by a constant. And bringing these together, we can write the full ground state wave function, psi 100, as equal to this prefactor times the exponential function. And again, a reminder that we derive all of these results in the linked companion videos, so check them out if you want to know where the expressions come from. These diagrams are a depiction of the ground state wave function of the hydrogen atom. The figure on the left shows the radial part of the ground state wave function. It has a maximum at the origin and then decays exponentially away from it. The figure on the right shows the angular part, which is the y00 spherical harmonic, and it is a constant. If you need to remind yourself of how to draw spherical harmonics, then check out the corresponding video that we have linked in the description. But just briefly, spherical harmonics depend on the angular variables theta and phi, so we can plot them on the unit sphere, and we use a red, white, blue color gradient scale with red corresponding to positive, white is 0, and blue is negative. And in this case, we get a uniform red sphere because the y00 spherical harmonic is a positive constant. So overall, the ground state wave function of the hydrogen atom takes its maximum value at the origin of the potential and then decays away from the origin in an isotropic manner. Next, we're going to explore in some more detail what we can learn from this ground state wave function, and in particular, we're going to focus on the proton-electron distance. The first question that we ask is, what is the probability of finding the electron at a given position vector r measured from the proton? And before we answer this question, we need a clarification. As r is a continuous variable, then a precise value of r is basically meaningless. What we should really ask is, what is the probability of finding the electron around r within the volume element dr? We're going to call this probability capital P of r dr, and it is equal to the absolute value of the ground state wave function squared, times a volume element centered at r. This should all be very familiar. We're simply using the standard interpretation of the absolute value squared of a wave function as providing the probability density of the position of a particle, and then multiplying by the volume element to obtain the probability. Spelling out the ground state wave function, we can rewrite this probability in terms of the radial part and the angular part and the volume element. We can also insert the expression that we have for the wave function at the top here, and we end up with this expression. Finally, we can spell out the volume element in terms of the spherical coordinates r, theta, and phi, and rewrite the probability like this. Now, you'll probably agree with me that this expression is not particularly enlightening. We could put some values in for the position r of the electron with respect to the proton here, and then evaluate the actual probability, but we wouldn't learn that much. One of the reasons for this is that the ground state wave function of the hydrogen atom is isotropic, which means that it is the same in any direction. Mathematically, this is reflected by the fact that there is no explicit angular dependence on the wave function up here. And this suggests that to make progress, it will be more useful to focus on the radial coordinate only, and this is what we will do next. So the next question we ask is, what is the probability of finding the electron at a given distance r from the nucleus? And note that here we're talking about the scalar distance r from the nucleus, and not the vector position r that we were discussing in the previous slide. Before we answer this question, we need the same clarification that we had in the previous slide. As the scalar distance r is a continuous variable, what we should really ask is, what is the probability of finding the electron at a distance in the interval r and r plus dr from the nucleus? we're going to call this probability lowercase p of r times dr. And it is equal to the absolute value squared of the radial function times the infinitesimal radial element. And when we only consider the distance from the origin, we need to average over all possible angular directions, so we need to integrate over the angular parts. Let's first focus on the angular integrals. We can use the fact that y00 is equal to the constant 1 over square root of 4 pi to take its square, 1 over 4 pi, outside, followed by the integrals over the angular coordinates. These integrals give the solid angle of the full 3D space, which is 4 pi, and we end up with 1. Inserting this result inside the probability of finding the electron at a distance r from the proton, we get the absolute value squared of the radial function times r squared dr. So what does all of this mean? The probability of finding the electron at a distance r from the proton, p of r times dr, is equal to this expression. In this expression, P of r is what we call the probability density of finding the electron at a distance r from the proton, and it is given by the square of the radial function times r squared. We can find an explicit expression for it by plugging in the value of the radial function for the ground state we have at the very top here, and we get this prefactor times r squared times this exponential. This expression gives the probability density associated with finding the electron at a distance r from the proton, irrespective of the direction. And this probability density is what we will use next to learn more about the ground state of the hydrogen atom. The diagram on the left shows the probability density that we've just derived for finding the electron at a distance r from the proton. As a reminder, in the diagram on the right, I'm showing again the radial part of the ground state wave function, which has a maximum at the origin and decays away from it. Now, at first sight, these two plots may look inconsistent. How is it possible that, given the shape of the wave function, the probability of finding the electron at a distance r from the proton has the shape shown on the left with a clear maximum some distance away from the origin? To properly understand this behaviour, we need to remember that we really have a 3D system, and apart from the radial direction shown in these plots, we also have angular directions. This function p on the left shows the probability of finding the electron at a distance r from the proton, irrespective of the direction in which we look. That means that when we consider an electron at a distance r from the proton, this electron could be at any point on a sphere of radius r centered on the proton. As we move further away from the origin, the surface of this sphere grows, and therefore the number of positions in which the electron can be also grows. Mathematically, the growth of the spherical area as we move away from the origin is captured by this r squared term here. We then need to combine this purely geometrical effect with the actual shape of the wave function, which describes an exponential decay away from the origin as encoded by this term. The combination of these two effects leads to this diagram, where the volume effects dominate at low radii, and the exponential decay takes over for larger radii, with a turnover point in the middle that leads to a maximum in the probability density. To find the location of this maximum, all we need to do is to evaluate the derivative of p and set it equal to 0. Explicitly, the derivative takes this form, and we can evaluate it using the chain rule, and we get the prefactor, the term involving the derivative of r squared, and the term involving the derivative of the exponential. We can take this as a common factor, multiplying by 1 minus r over a 0. Going back to our derivative at the top, we get this condition for the maximum.
We can cancel these terms as they're positive, and we find that the maximum is for r equal to a0. And this means that the maximum here is located at a distance a0 from the origin. And what is the meaning of this? The most likely proton-electron distance in the ground state of the hydrogen atom is a0, which is called the reduced Bohr radius. Remember that we initially introduced the reduced Bohr radius in the video where we solved the eigenvalue equation for the hydrogen atom Hamiltonian, and at that point it was a purely pragmatic definition that helped us to simplify the notation somewhat. We now see that that reduced Bohr radius has actually a very important physical meaning. It describes the typical size of the hydrogen atom, which is given by the most likely distance between the electron and the proton. Okay, now that we've seen that the reduced Bohr radius has a very important physical meaning, we should evaluate its actual numerical value. Remember the definition of a0 as equal to this expression in terms of fundamental physical constants and in terms of the reduced mass of the proton-electron system. To consider its numerical value, we again need the reduced mass mu, which we said earlier is equal to 9.104 times 10 to the minus 31 kilograms. We also need the elementary charge, which has this value, the permittivity of free space, which is this, and the reduced Planck constant, which is this. Inserting these numerical values into the expression at the top, we find that the reduced Bohr radius is equal to 5.3 times 10 to the minus 11 meters. Just like we found in the case of the ionization energy, SI units are not ideal to describe atomic parameters, and we will instead use the angstrom, which is abbreviated as a capital A with a small circle at the top. 1 angstrom is defined as equal to 10 to the minus 10 meters. So, with those units, the reduced Bohr radius is equal to 0.53 angstrom. Right, so that is the typical size of the hydrogen atom. While atomic sizes vary depending on the element, they are often compared to the size of the hydrogen atom and therefore described in terms of the Bohr radius. And for this reason, this is a good number to remember as you continue in your study of atomic physics, chemistry, and material science. To finish, we're going to explore how the kinetic and potential energies separately contribute to the total energy of the ground state of the hydrogen atom. To simplify notation, we will label the kinetic energy term with a capital T and the potential energy term with a capital V. We start with the expectation value of the Hamiltonian in the ground state, which we can explicitly write out like this. We can use the eigenvalue equation here to end up with the ground state energy as the ground state is normalized. From our earlier discussion, this is equal to the negative ionization energy. On top of that, as the Hamiltonian is the sum of the kinetic and potential energies, we can also write the expectation value of the Hamiltonian as equal to the expectation value of the kinetic energy plus the expectation value of the potential energy. Combining these two results, we get to this relation between the expectation values of the kinetic and potential energies with respect to the ground state wave function. Let's next separately consider the expectation value of the potential energy in the ground state. Spelling out the expression for the potential energy, we can rewrite the expectation value like this. We can also take this constant factor out, multiplying the expectation value of 1 over the magnitude of the position operator. So our next job is to evaluate the expectation value here, which we can first copy down. Using the position representation as spherical coordinates, we can rewrite it as the angular integrals, the radial integral, and then the integrand is 1 over r times the absolute value squared of the ground state wave function. Now recall that the ground state wave function has no angular dependence, so we can directly evaluate the angular integrals, which give 4 pi. We can also combine these terms together to get the integrand of the radial integral. Using the expression we got earlier for the ground state wave function, we end up with this integrand for the radial integral. At this point, we're going to use this standard integral, which you can look up in the usual integral tables or just evaluate it directly. In our case, p here is equal to 1, and alpha is equal to 2 over a 0. So with this, we can evaluate the expectation value of 1 over r to get the prefactors arising from the angular integrals and the wave function prefactors, times the result of the standard radial integral. Finally, the expression simplifies to just 1 over a 0. The end result is really very simple. The expectation value of 1 over r in the ground state is the inverse of the reduced Bohr radius. So inserting this back to our expression for the expectation value of the potential energy, we get this expression. Let's make some room. To make progress, we need to consider the ionization energy, which, remember, is equal to this. We can reorganize the expression for the ionization energy like this. And we now recognize the term in brackets as the inverse of the reduced Bohr radius, so that we can write the ionization energy in terms of the reduced Bohr radius like this. If we now compare this expression with this expression, we can conclude that the ionization energy is equal to minus 1/2 times the expectation value of the potential energy. And finally, we can write that the expectation value of the potential energy is equal to minus twice the ionization energy. So let's summarize what we have just found. First, we found that the expectation value of the Hamiltonian, which can be written as the sum of the expectation values of the kinetic energy and the potential energy, is equal to minus the ionization energy. Second, we've just found that the expectation value of the potential energy can be written as minus 2 times the ionization energy. From these results, we can now easily calculate the expectation value of the kinetic energy. From the top equation, the expectation value of the kinetic energy is equal to this expression. And inserting the value of the expectation value of the Hamiltonian here, and the value of the expectation value of the potential energy here, we end up with minus EI minus 2 times EI, which yields the ionization energy. So what does this mean? We can write the expectation value of the potential energy being equal to minus twice the expectation value of the kinetic energy. And this result shows that the magnitude of the potential energy contribution to the total energy is twice as large as the contribution from the kinetic energy for the ground state of the hydrogen atom. This relation is actually an example of a more general result known as the Virial theorem, and I encourage you to check out the video that we have linked in the description to learn more about it. But in short, the Virial theorem describes a general relation between the expectation value of the kinetic and potential energies when the system is in an energy eigenstate. These general relations are useful because they provide insight into complex systems without having to do any explicit calculations like the ones we've done up here. In the context of the hydrogen atom, this result will be valid not only for the ground state, but also for any excited state.
The analysis of the ground state of the hydrogen atom has led to some very important scales that play a key role across atomic physics. The first one is the ionization energy, which gives the typical energy scale associated with atomic systems. And the second one is the Bohr radius, which gives the typical length scale associated with atomic systems. And that's it for today. If you liked the video, please subscribe.